to go on to talking about what the magnetic field is when you're in the neighborhood of a circular current loop. But to do that, I want to take a little side trip here, and this is somewhere the book doesn't go, so you're going to need to follow closely. Although it's really not going to impact things dramatically, it just makes our work a little shorter, that's all. And that is to introduce you guys to the idea of cylindrical coordinates. The book actually does do this way back in an earlier chapter, but it's something that we get skipped over quite frequently in Physics 240, so you might not have seen it. Although you've probably seen cylindrical coordinates done somewhere else. The idea here is if I'm going to express the position of an event or an object, that red star there for instance, I can use my good old-fashioned x, y, and z coordinates. That means I'm taking so and so many steps along x unit vectors and so many y unit vectors and so many z unit vectors to get my r vector out of it. But an optional way of doing that is instead of using the x, y, and z, I can talk about the distance I am from the z-axis. So what I will do is come out from the z-axis, wrap around until I'm underneath the thing, and then go up to it. And the distance away from the z-axis, I'm going to use the Greek letter rho. Looks like a p, but it's a rho. The angle that I form with the x-axis that's swept out there is the angle phi, and the height above the xy plane is z. So instead of using x, y, and z, I'm using rho, phi, and z. Now, you may have seen other things than rho and phi used when you've done cylindrical coordinates in the past, and there's a lot of different ways of doing it. But one way or another, I have these three coordinates that represent this particular position. Now, the reason I'm doing this is because if I deal with things with cylindrical symmetry, for instance, a ring or a tube or something like that, these coordinates are going to be a lot more handy, as you'll see in a few minutes. What I'm curious about right now, though, is what happens to the unit vectors. And what I mean by unit vector is how many steps, if you will, along a particular direction. So what I need to have good unit vectors are things that have a length of 1 and that are orthogonal to each other so that they're independent of each other. So x, y, and z are obviously independent of each other. So if I look at this, the step in the forward direction in the rho direction is going to be that little purple vector right there. A forward step in the phi direction is that little purple vector. Now notice these two guys depend on where I am. As I rotate around the z-axis, phi and rho are going to point in different directions. So I no longer have unit vectors that are constants. That's going to be a little tricky thing to deal with, and there's one impact of it that's going to show up in just a second here. But it's not something I want to worry a heck of a lot about, because I want to go on forward here and lift up to where my event is and point out that there's a unit vector z that's the same as it ever was. Now, these unit vectors are orthogonal to each other. That means if I take cross products between them, they should give each other, just like they did with x and y. And in fact, that's what happens. If I look at rho and phi and curl my fingers the right way, I notice it gives me z. If I look at phi and z and curl my fingers the right way, it gives me rho. And if I look at z and rho and curl my fingers the right way, it gives me phi again. And negatives on the interchanges, just like we had with x, y, and z. So kind of circle those guys and hang on to them, because I'm going to be pulling two of them back into play in just a minute here, because what I want to do is look at this circular loop of current here. Let's say I got current running around this guy. If you were standing above it looking down on it, the current would be running counterclockwise, so that means that the current loop is oriented upward, if you will. And I'm going to imagine for a second that I'm going to go out here to a position on the edge of this current loop on the circle. The radius of the circle is capital R, and that particular position I'm looking at, I'm going to view from a height above the center of the ring Z. Now, if I look back at that position, it will give me a certain amount of a magnetic field because of the current that is at that little step that I'm pointing to right now. That step is ds, and the ds is equal to r d phi in the phi hat direction. Notice that going around the circle is always going to be going in the phi hat direction. That's the reason for using these unit vectors now. Now, the thing I can do is look at what the r is. R is negative r in the rho hat direction and z in the z hat direction. If you look at the way r is pointed, you'll notice I'm going backwards r in the rho hat direction, and I'm going up z in the z hat direction. And the unit vector in the r direction is just going to be that divided by little r. Now, I want to point out, this may look like it's a constant, but it's not, because as I said, the rho hat vector actually does depend on my position around the ring. But for now, let's just play with it and go along for the ride. So let's take our ds and our r hat and put them into ds cross r hat and see what happens. Well, if I distribute out the cross products the way we've done before, I have minus r squared over r times d phi times phi hat cross rho hat. Remembering phi hat cross rho hat is going to give me negative z hat, so I'll be able to make that substitution in a second. And then I have r times z over little r d phi times phi hat cross z hat. And if I take phi hat cross z hat, I'm going to get rho hat. So let's go ahead and make those substitutions. I put in my z hat and my rho hat. I get this. Now here's where the dependence of rho hat makes things interesting. Z hat is the same everywhere around that circle. So if I start to integrate this guy and add up all the little dBs that I'm getting from every little bit of ds as I go around the circle, the z hats are just going to add one to another fine. They're all pointing upward. But the rhos are actually going to be pointing in different directions. In fact, you can imagine that I'm going to have a rho hat that points away from the center of the circle where I am now. But if I flip around to the other side, I'm going to have an equally large rho hat that points away from the circle the other direction. So therefore, as I scan all the way around that circle, all these rho hats are going to cancel each other out. I'm going to have as much pointing to the left as the right and to the end of the out. So in any case, I don't have to worry about that anymore. The only thing that matters in my ds cross r is going to be the r squared over r d phi in the z hat direction. So let's plug that in. dB, the element of magnetic field that I'm getting from that little chunk right there, is going to be equal to mu naught I r squared over 4 pi times d phi over r cubed in the z hat direction. Now r cubed I can make a substitution for, because r cubed is just the cube of that little r, and little r is z squared plus r squared square rooted. So r cubed is z squared plus r squared to the 3 halves. All that is constant. I'll go ahead and pull that out of the integration when I integrate around the circle. So now all I'm doing is adding up all those bits of dB around the circle as I go on d phi from 0 to 2 pi to make the full circle. 0 to 2 pi integrated just gives me 2 pi, which cancels part of that 4 pi in the denominator, and I wind up with a magnetic field strength at some height z is mu naught I r squared over 2 times r squared plus z squared to the 3 halves in the z hat direction. The book actually does this slightly differently. They use a little different notation, and they also orient it along the x-axis instead of the z. I prefer to do it along the z because then I can get away with using cylindrical coordinates. The book also uses some geometric arguments. They come to the same conclusion that I do, that there's no reason to worry about anything other than the z component. So if you want to look at how the book does it, that's probably not a bad idea. Either way, this end result is what we're going for. One other thing I'll point about this is if I were to take a limit here, as as z goes back to 0, I can figure out what the magnetic field is at the center of the ring, and that is not 0. The other thing to point out is that the value up top, r squared, is always positive, and the value in the denominator, r squared plus z squared to the 3 halves, is always positive, and everything else is positive, so therefore the magnetic field always points upward as I pass through this thing. It may be weak as I go to infinity, but it's always on an upward line.